Now, as far as you're concerned, neutrinos and antineutrinos. The beta minus decay, the particle is an antineutrino, which is snake with the lid on the box. The beta plus decay, it's a neutrino, which is snake with no lid. Neutrinos have no charge, no mass, they travel at the speed of light, and they have energy and momentum. Hooray! Even though they have no mass, and they travel at the speed of light, they have energy and they have momentum. Now we're dealing with antimatter particles here. So they're different in terms of charge, but otherwise identical. So the neutrino, its antiparticle is the antineutrino, and the electron, its antiparticle is the positron. So antiparticles are what we call antimatter, and when you mix matter and antimatter together, you end up getting pure energy, hence the whole concept of the sci-fi antimatter bomb. Ionizing power. An ion is an atom that's chemically reactive because it has too many or too few electrons. Now, the ability of radiation to ionize things is very important. Alpha radiation, with its +2 helium nucleus, very high ionizing power because it's quite charged, so it has the ability to really mess with electrons. But it's got low penetration because on the atomic level it's actually quite bulky and it's not that quick. It easily collides with other atoms, and as a result, because it's so big, it's able to lose all of its energy quite quickly, so it never really penetrates very far, but it can do quite a lot of damage. Beta particles have less ionizing power, and they have a greater ability to penetrate because they're a lot smaller and they have less charge. They're positive or negatively charged. And gamma has really low ionizing power but really deep penetration ability. Now, you'd think, well, gamma rays are right up the other end of the spectrum. Why would, something like a gamma ray have really low ionizing power? Well, it all comes down to the chance of collision. Whatever it is the gamma ray is going to collide with has to be in the particular space and time to be in the way of the gamma ray. And so hence why they have such deep penetration ability. But when the gamma ray hits, it will ionize, but it's just the chance of it hitting something is quite low. And the last one, neutrons, fast-moving neutrons, they'll get through heaps. You need, like I said, 5 meters of concrete barriers in nuclear reactors just to stop those neutrons. Now, radiation, often you might see questions in the exam relating to the path of radioactive particles in a magnetic field. In this case here, you can apply the right hand rule. Gamma ray goes all the way through because it's just completely uncharged. Here you've got your alpha particles, so that's positive charge. So you do the direction of conventional current, which is the flow of positivity. The magnetic field's going into the board, and therefore it'll get pushed up. The beta plus particle, i.e. the positron's also getting pushed up, but it will go further quicker because it weighs less, so it's got more of an effect on the force, and the electron will be equal and opposite. Here we see the electron going towards the positive plate of two parallel plates, and the alpha particle and the beta plus particle heading towards the negative plate. Ionizing radiation. How is it fun? It's got energy to knock electrons out of orbits. Alpha and beta particles are ionizing, beta plus and beta minus, neutrons, gamma rays and X-rays. Now, not all ionizing radiation comes from a nuclear transmutation reaction, and X-ray is a perfect example. That comes from an X-ray tube. Then there's all this non-ionizing radiation like radio waves, microwaves, and visible light, which don't contain sufficient energy to damage or knock electrons out of orbits. Other forms of important radiation include gamma rays from cosmic radiation, charged particles in the solar winds, and most of that is stopped by the atmosphere and the magnetic field of the Earth. And then we got your human-generated radiations, which are your X-rays, microwaves, and so on, radio waves. And how does it work? So the ionizing radiation is going to knock an electron, like a valence electron, out, bury it in an ion, or it strikes a chemical bond and splits molecules apart and creates these things called free radicals, which are like oxygen. Example would be the oxygen free radical. That if it's just oxygen by itself, not bonded with another molecule, it's really reactive. And if you have the radiation strike somewhere in, say, for example, the nucleus of a cell, and it creates a free radical, well, the nucleus of the cell is full of DNA, and so there's this chance that then the DNA will just get all damaged by the reactive element. Things aren't supposed to get all sort of spontaneously reactive in the middle of your cell. When you start creating things like that, you really mess with the biomechanics of the cell, the biochemistry of it, and you can either program it for death or it becomes cancer or several other effects. I mean, hell, you could even strike DNA and then knock bonds out of that. Now, DNA will normally fix itself. So, you know, your A, T, G, and C here has self-repair features that when the DNA has a mistake, something will, you know, like one of the polymers will come along, what do they call them, enzymes, and they'll fix the DNA. But sometimes if you stuff that genetic code up and you try and have a baby or something, then you get all these radiation defects, because if you start sticking the wrong letters in there, you start producing the wrong stuff. Hold on, I've got a phone, someone at the door.